We'll just wait for a couple of more minutes to see if everyone is joining and then we'll begin. So I think we'll begin. About 25 people here. We'll begin. So hello everyone. This is Tanya. I'm one of the TAs aircraft design course taught by Professor A.K. Ghosh. So we'll be meeting every Tuesday. People coming in. Okay. So we'll be meeting every Tuesday. This was just a rescheduling issue. So we'll discuss the contents of the previous week. So now we'll discuss the contents of week 1 and it'll help you solve your assignments which are scheduled on Wednesday. So yeah, we'll just start with the contents. So before that, have all of you gone through the lectures, week 1? Am I audible? Okay, yeah. So have you all gone through the contents of week 1? Okay. So let's just go over some of the equations that we may use during the course of the assignments or any questions. These are all from week 1 and a few from week 2. We'll just go over the equations. CL, just a minute. Okay. So the first equation is the equation of the lift coefficient. CL equals CL naught plus DCL upon D alpha into alpha, where CL naught, so this is your typical lift curve. CL versus alpha. Okay, so can someone tell me what CL naught is? CL at 0 degree. And in this graph, what is the value? 0, yes. So what kind of an airfoil will it be? Symmetric. Yes. Now if it's a cambered airfoil, how will this graph look different? What will be the difference? CL naught will be positive, exactly. So you'll have something like this. And this is CL naught. Okay. And the slope of the graph is CL upon D alpha. Okay. The next equation is the drag polar. CD is CD naught plus KCL square. So what is CD naught and what is KCL square? Do they have some names? Do you recall that? CD naught, KCL square. CL is the lift coefficient, yes, but okay. So when you say zero lift drag, so it's called parasitic drag. Okay, so it's the drag that's always present. Yes. Okay, parasitic and induced. So it's parasitic and this is induced. Okay, what do you mean by induced drag? We'll go over this in detail in one of the questions, but I just want to know what you think. Induced drag. Okay, anybody else wants to add to it? This is induced. Okay, so drag. What is downwash? Can you try and explain? Okay, yes, perfect. That is the induced drag. Okay, so we'll go over this in detail in one of the slides, but just want to know what you thought about it. Okay, so the next equation is the thrust required equation for a steady level flight. So thrust required is weight upon L by D. Sir has derived this equation multiple times in the lectures. Then we have velocity. Velocity is given by this equation. And similarly, if you plug in CL max instead of CL, you have V stall. What is stall? Um, okay, so if we take lift equals weight, so that is the steady level flight, right? So at that flight condition, you have thrust equal to drag, and using these equations, you found out this thrust required and this V. So you get what do we so half rho V square SCL equals lift, and in this case, it equals weight. So that's how you got this equation for V. 2W upon S by rho CL. Correct? That's how you derived V. That's this V. So what is V stall? How is it different from this V? I took L equals W and I got this equation for velocity. How is V stall different? minimum velocity required to maintain L equal to W. Yes. So what happens if you fly below V stall? Bank. Okay. Okay. So bank is. Huh. Okay. Yes. So I'm trying to understand aerodynamically why do you think it happens? So if it's an airfoil, so you have. I'm just taking a cambered airfoil. So it's flying at some alpha. All right. So at stall, alpha becomes alpha stall. What is this alpha stall? So if I take this graph, this value corresponds to CL max, right? So this is CL max. So this should be alpha stall. So there is a sudden drop in lift beyond alpha stall. Why is that drop in lift? So I'm not sure if this is clear. So this was your original graph. Let me just draw that again. 1 minute. So there's a sudden drop in lift after alpha stall. Why do you think that happens? Due to increase in drag. Why? Flow separation. Okay, what flows? Can you try and explain that? Correct. So when it's flying at regular condition, you have air flow over the wing, something like this. Okay. Now when it increases, the angle of attack keeps increasing and goes to alpha stall, something like this. Your flow over the wing tends to separate from the surface. So there is this boundary layer separation, such that at that point the airfoil does not generate enough lift to maintain the weight, does not generate enough lift to fly the aircraft. So beyond alpha stall, if you deflect it beyond alpha stall, it will not generate enough lift to balance the weight. That is why there is a sudden drop in your CL versus alpha because of flow separation. He's right. I'm not sure who said it, but he's right. It's the right answer. There's a boundary layer separation or flow separation, and there is no. So how is lift generated? The air flows above the airfoil and below the airfoil, and what causes this lift generation? What causes the upward force? Difference in pressure. So if there is a flow separation in the upper surface or any of the surfaces, at some point the lift generation would not be sufficient to balance the weight, and hence there is a sudden drop in lift. So that point is known as stall. All of you had given varying answers, but they're all right. Stall is when it's the minimum velocity required to maintain L equal to W. Less than that, it will not produce enough lift. So similarly, beyond alpha stall, if you fly it beyond alpha stall, it will not produce sufficient lift. Okay, so let's move on. So this is just okay. So this is just a comparison between the two cases that are mentioned in the lectures. So the first one is minimum drag or minimum thrust required. So TR min. They're both corresponding to the same thing. And the other one is the minimum power. Okay, so minimum drag or minimum thrust required also corresponds to maximum range, and minimum power corresponds to maximum endurance. And the two conditions are just given here, just for comparison. So for this minimum drag, you have CL by CD max. So Sir keeps mentioning the L by D max. It also corresponds to minimum drag. When it is minimum drag, CL by CD will be maximum. And when it is minimum power, CL raised to 3 by 2 by CD, that ratio will be maximum. Okay. So at these two conditions, the values for CL and CD are, you must remember these. These are used vastly in your design course. So CL for the minimum drag condition or minimum thrust required condition is root upon CD naught by K. For minimum power, it is 3 CD naught by K, root upon 3 CD naught by K. Similarly, for the drag, you just have to remember the CL. Drag you can easily derive from your drag polar equation. So if I just write CD equal to CD naught plus KCL square and plug in the values for each case. So let's just do it for minimum drag. So it will be CD naught plus KCL square. So it's K CD naught by K. In turn gives you 2 CD naught. Okay. So you just have to remember the CL. CD naught, you can just plug it into your drag polar equation and find out. So similarly, if you do it for the minimum power condition, you will find that CD is 4 CD naught. All right. Okay. Now let's start with a few questions. So with the increase in height, the density and temperature will increase, decrease, remain same, or none of these? Decrease. Okay. Any other answers? Decrease. Okay. So before this, okay, before this we need to look into the standard atmosphere model. Here they haven't mentioned whether it's troposphere or stratosphere or anything. So if it's not mentioned, you assume troposphere, and all of you are right, it does decrease. So let's just go over the standard atmosphere. Have all of you done the aircraft performance course? Okay, okay. So most of these concepts are covered in the aircraft performance course. So if you have any doubts, just refer to that course. If not, we'll discuss in the class. And sir also very basics. But in case there are some concepts that you find unclear, please do refer to the aircraft performance course. Okay, so let's start here. Here, this is a graph between the altitude and the temperature. Okay, so we can see that the tropospheric limits are from 0. Oops, 1 minute. Yeah, so tropospheric limits are from 0 to 11 kilometers. All right, so there the graph has a, it reduces, right? The temperature reduces in that range. Correct. Density also, as the altitude increases, the density reduces. That is given. But this is the graph for the temperature. Okay. So in the tropospheric region, the graph has a negative slope. That slope is referred to as, it's denoted by lambda, is referred to as lapse rate. Okay. So the reduction, the rate of reduction of temperature in the region is referred to as lapse rate. So what about in the region from, let's say, 11 to about 20 kilometers? What would the lapse rate be? Lapse rate is the slope of the graph, okay? So it's the rate of reduction of temperature, rate of change of temperature. 1 second. What? I couldn't hear you. Can you repeat? Yes. So in the range of 11 to 20 kilometers, what would it be from the graph? 0, exactly. It will be constant. So dt by dh will be 0, correct? So in this case, your lambda would be 0. In the tropospheric region, it would be a negative value. Okay, so it reduces. And then so on and so forth, depending on the graph, the lapse rate becomes either positive, constant, or 0. But you must remember the model, at least till stratospheric range. Okay, that's still about 50 kilometers. Just know the general variation. Okay, so yes, you are right. For the question, with the increase in height, both the density and temperature decreases. All right. Let's go to the next question. Which airfoil is preferably used for design of horizontal and vertical tail? Okay, it hasn't. Okay. Which airfoil is preferably used for design of horizontal and vertical tail? Okay, symmetric. Someone said symmetric. Can you try and justify your answer? Why symmetric? Yes. So what you said is right. The main purpose of these horizontal and vertical tail is to produce stability, is to contribute towards stability and not to produce lift. So what is the producing structure of the aircraft? Wait, yes. Yes. So is everybody okay with the answer that he gave? Why we are using symmetric? The answer is symmetric. He's right. His answer is also right. So is everybody okay with it? Okay. So just stop me at any time when you are not okay with the answers that, or the answers are unclear. Okay. So yes, symmetric airfoil is preferred for the design of horizontal and vertical tail because their main property or main contribution is towards stability and not to produce lift. Okay, so for the wings we use cambered airfoils because the main property of the wing is to produce lift. Now, how is a symmetric airfoil different from cambered airfoil? Why do we prefer cambered for wings? Yes, the surfaces are different. I'm correct. Yes. So the pressure difference is more and hence the lift produced or the force produced is more. Correct? Yes. So that is the right answer. That is why the cambered airfoil produces more lift. Cambered airfoil in fact produces lift even at zero angle of attack. This is what we saw in the first slide, right? So for symmetric, let me just draw it here. This is CL versus alpha and this is for cambered. Something like this. So CL versus alpha. So even if your wing is at zero angle of attack, your cambered airfoil, if you're using a cambered airfoil, it will produce a lift, right? So it has a CL naught. So it produces lift even if it is at zero angle of attack. Whereas symmetric airfoil produces no lift at zero angle of attack. And the reason that he has given is correct. The pressure difference of across a cambered airfoil is more, and hence the force generated, the lift generated. Lift is nothing but the aerodynamic force generated. What is the other aerodynamic force generated? Why would they? So one, due to the pressure difference, the pressure below the surface of the wing is more than the pressure above the surface of the wing, and so it produces lift, right? There is another aerodynamic force that's produced when you move any body in an air in some or there's some oncoming velocity or you move your body in air. One force is lift. What is the other force? Drag. Exactly. So there's a drag force also generated. So these are your two aerodynamic forces. Okay, let's move on. Okay. Wing loading. Wing loading was W upon S. Wing loading will affect only stall speed, only climb rate. What is the right answer? Excuse me. Both A and B. Can you try and tell me how? Fx stall speed, we have the direct formula, right? So the first slide we had the stall speed. It was root of W upon S by CL. So stall speed, yes, direct relation. What was climb rate? You can you try? Yes. Okay. So that is thrust into velocity. Okay. So when you replace all of these terms, I think I've written it somewhere. Yeah. So these are the two equations which all we know directly. Rate of climb is exactly what he said, power available minus power required by W. And when you replace or substitute the terms, this is the final equation for rate of climb. And you have W upon S there. So wing loading directly affects both stall speed and climb rate. Okay. So the answer is both A and B. Now let's look at some other question. Okay. So an aircraft wing has a positive cambered airfoil E124 Epler series. Which of these following graph correctly represents the graph between CL versus alpha? A. Why A? CL naught is positive and you've mentioned a positive cambered airfoil here. So your CL naught would be positive, greater than 0. Alright. So what about case B? Case B represents what kind of airfoil? Symmetric. So this was cambered, this was symmetric. Case C, negative cambered. What about the last? So the spoilers in race cars, right? Yes. Anywhere else do you think we use negative camber? I'm not sure of the answer, but can you think of some cases where we use a negatively cambered airfoil? Okay, canard again I think would be symmetric or okay. Let's just look this up and we'll see it in the next class. Negative cambered airfoil, where do you think it's used? Just look it up and we'll go over it in the next class. Okay. What about case D, where there is constant lift for any angle of attack? What is that? Is there such a body? Is there such an airfoil? Is there such a body that produces constant lift for any change in angle of attack? Yeah, there is no such device. Even if you move a flat plate in air, if you change the angle of attack, it will produce varying lifts. It will not remain constant with angle of attack. Okay, case D doesn't exist. So the answer is right. Case A. That is for positive cambered airfoil. Okay. Now, which of the following statements are true for a typical flight profile of quadrotor UAV, fixed wing UAV? What is the difference between these two? Like quadrotor UAV and fixed wing UAV? Okay, yes. Okay. So fixed wing UAV is similar to a regular aircraft. Quadrotor has four rotors. You're right. So now, what can you comment about their thrust loading, thrust to weight ratio? Just think about it. Think about the quadro. Fixed wing, we know we have discussed, right? Thrust loading is less than one, right? For a fixed wing UAV, for an aircraft, it's less than one. Less than one for fixed wing. Okay, so during climb, I think sir had given this equation, right? So let's just write that down. What was it? Second. So you had for climb, the equation of motion was t minus d steady climb. Okay, w sine gamma equals 0. So here you get divided throughout by weight, and you get it is a d upon w plus sine gamma. Now, if you take a small gamma value, you get something typically around. Just take a very small gamma value, right? So you get something around zero point 0.1. I think this is an example that sir did in the class, around zero point 0.1, and your d upon w is nothing but this inverse of the CL by CD ratio, right? So CL by CD is somewhere usually around 10, 15, something around there. So this is nothing but 1 by approximately, right? So 1 by CL by CD plus zero point 0.1. So this will always be a value less than 1, correct? So for a fixed wing, this is the typical range. So this will come to around, if you just take 10, how much will it be? Excuse me. So it will be less than 1 at all points, right? Is it clear? Okay. So now so for a fixed wing UAV, it will be less than 1. We know that. Now what about for a quad rotor? Thrust to weight ratio for a quad rotor. Just think about it. Quad rotor has four. What do those rotors produce? Balance the weight, correct. So they produce thrust. Each of those rotors produce thrust, and the overall thrust balances the weight, correct. So what would the excuse me weight ratio be? The quad rotor, if it is hovering, it will be 1. If it's climbing or moving forward, it will be greater than 1, right? So it's greater than or equal to 1. Yeah. So the answer would be here, D, correct. So So all of these quad rotors, all the four rotors produce thrust in the vertical direction and then they balance the weight. How does the quad rotor move forward and or turn or anything? How does the quad rotor move forward? Correct, correct. So you control the pitch and so the thrust is aligned in the forward direction and then it moves forward. Correct. How do we roll the aircraft, the quad rotor? Yes. Correct. So you just increase the RPM of one side. Yes. And what about yaw? Correct. Perfect. This is right. So is everybody clear with this? This is not the focus of this course, but I just thought it would be fun. Yeah. Okay. Yes. Ruba Shini, can you want to ask a question? Did you have a question? Okay. So we'll just move ahead. What is the primary control for angle of attack? Elevator. Okay. Any other answers? Okay. So there is a slight issue with this question. So what is angle of attack? Angle of attack is alpha. How is it defined? What is angle of attack alpha? With respect to the chord, correct. So it's the angle between V infinity and the chord line. Okay, can you control this? Chord line, you fix your wing on the aircraft at some angle. So it is, the chord line that is fixed, your airfoil is fixed, and V infinity is not in your control. So can you control angle of attack? V infinity is the ambient velocity, oncoming velocity. Can we control that? Okay. So when we pitch up or pitch down the aircraft, we change the attitude of the aircraft, right? Effectively changing angle of attack, but we can't say controlling angle of attack. So what is the angle that the elevator controls? What is it called? The attitude, the orientation of the aircraft has, like, there are three angles that we control, right? About the three axes. Yes. So what is the angle that the elevator controls? Pitch. Correct. So this question should ideally have been, what is the primary control for a pitch? We do effectively change the angle of attack, but it's not something that we can control. Effectively, yes, angle of attack changes when the aircraft eventually pitches up and then the relative direction of the velocity changes. But we don't control the angle of attack. We control the pitch. So it should have been pitch. So it's the angles that we control are roll, pitch, and yaw. So in this case, the elevator controls the pitch. What does the rudder control? Yaw. And the aileron controls the roll. Okay, so the control surfaces control these three angles, which eventually changes the angle of attack. But we control these three angles. These are the attitude of the aircraft. Okay, moving on. Yes, did somebody? Primary control for angle of attack with question should have been primary control for angle for pitch, and that would still be elevator, right? Yes. So it will just be added by the pitch. So we will just denote it by like, so it will just be alpha plus that theta pitch. And if it is roll or yaw, it would be in the other direction. So the component of velocity that is in that direction will be contributing towards the, so it will be what, beta plus the roll term, roll or yaw. So it will just, effective angle of attack will change, but the original angle of attack remains. That only changes if the velocity's direction changes. So if there is a gust or something. So yeah, so this is just a depiction of how the elevator changes the pitch. So in this case, the elevator is deflected upwards. So there is a downward aerodynamic force. So the aerodynamic force generated, in this case, it's something like a negative camber. It introduces a negative camber. So it produces lift in the downward direction. So it's a downward aerodynamic force, which causes a pitch up movement. Similarly, if you were to deflect the elevator down, elevator is generally symmetric airfoil. Okay, so if you deflect the elevator down, you've introduced a positive camber, which then produces a lift force in the upward direction, and it would produce a pitch down. Okay, so that is how the elevator controls the pitch or the orientation of the aircraft. Okay. Which one is correct about static margin at neutral point of aircraft? What is static margin? CGN? Yes, CG neutral point, exactly. So at neutral point, what is static margin? Equal to zero. Correct. So static margin, I've just written down the equation for static margin here. It is the negative of the slope of CM versus CL. And you are right, it is the difference between neutral point and CG. So for a stable aircraft, what would this quantity be? Positive, zero, negative? Static margin for a stable aircraft, typically what would it be? Uh, I did not get you. Can you repeat? Less than zero. Okay. So, so if this is the fuselage reference line of the aircraft, and this is the neutral point, for a stable aircraft, where should the CG be? In front of the neutral point. Okay. So here. So if this is your reference point, this is your XCG, and this is X neutral point, right? So static margin is XNP minus XCG. So for a stable aircraft, would that quantity be positive or negative? Positive, yes. So for a statically stable aircraft, your XNP minus XCG value or the static margin would be positive. For an unstable aircraft, static margin would be negative. So before we get into all of that, what is stability? How do we define stability? Static stability. Okay, return to its equilibrium position. Okay, so what is equilibrium position? Tendency of an aircraft to return to equilibrium position is static stability. What is in our aircraft case? What is, or in any case, what is an equilibrium point? You are right. So if it's disturbed, if it's flying in some steady level condition and it's disturbed by a gust, if the aircraft is statically stable, it will tend to come back to its equilibrium point. What is equilibrium point? Net force, yes. So Prajwal is right. Net force and net moment is zero. So one such condition for your aircraft is your steady level flight, where lift equal to weight and thrust equal to drag. So if it's flying at that condition and it's disturbed by a gust, tendency of the aircraft to bring it back to equilibrium position is static stability. What do you think is dynamic stability? So yes. So over a period of time, whether or not it comes to equilibrium point is dynamic stability. So if you have some, uh, the baseline is your neutral equilibrium point, and you've disturbed it, does it over a period of time, does it come back to the equilibrium point is dynamic stability. There are some systems that go, they diverge, they become unstable. But there are some systems that oscillate and over a period of time, they come back to equilibrium. So if the system does come back to equilibrium point over a period of time, it is dynamically stable. Okay, so static stability is just the tendency of the aircraft to come back to equilibrium point. Equilibrium point is where sum of forces and moments are zero. One such point is the steady level flight, or something that we refer to as trim. Trim is also equilibrium, where in the pitching moment, in the longitudinal case, your Cm versus alpha graph is something like this. So where the net moment is zero, this point is this equilibrium point. You refer to it as trim. Okay, so these are equilibrium points. Okay. Which one is generally responsible to generate lift of an aircraft? We had discussed this, so which one do you think is the right answer? Yes, it should be all of these. Angle of attack directly we know. So a CL is CL naught plus CL alpha into alpha. So angle of attack directly contributes towards lift, right? Then wing incidence angle. So what is wing incidence angle? Correct. So the angle at which the wing is attached onto the aircraft. So it will also contribute towards angle of attack, right? So if this was your fuselage reference line and you've fixed your wing like this, and you fixed your, if in other case, the, excuse my poor drawing, but if you've fixed the wings at different angles, this will obviously produce more lift, right? So it has an initial angle with respect to oncoming velocity. So it will produce more lift. So that is your wing incidence angle. So both wing incidence angle and wing angle of attack contribute. Then wing camber. Camber, we had just discussed how the positively cambered airfoil obviously contributes towards more lift than the symmetric airfoil. Okay, so yes, the answer is all of the above. All of them contribute towards generating lift of the aircraft. Okay, yeah. So this was just an example of how. Yeah, so this is how it shows that even if you move a flat plate in the oncoming velocity, it produces lift, right? What is the difference between these two cases? Flat plate and an airfoil. Why is the airfoil better? We just discussed that the pressure difference is more. Okay, so what happens is that both the flat plate and the airfoil produce aerodynamic forces when subject to an oncoming airflow. It just so happens that due to this pressure difference, the lift force denoted here by FL is less in the case of flat plate as compared to drag. But in a cambered or even symmetric airfoil, when compared to flat plate, produces more lift than drag at an angle of attack in oncoming velocity. Okay, so this is just for that demonstration. Okay. Okay, so here the question that I asked right in the beginning, what is induced drag of an airfoil? What was induced drag? Somebody had mentioned something about vortices, that is right. So can you try and answer this? Induced drag of an airfoil. Finite but not zero. Can you tell me why? Okay. So why are the vortices produced? Yes, so at the tip there is this, so I'll just show you. Yeah. So what he said is right. The vortices are produced because, so let's just look at this figure first, okay? So when the air flows above the wing, it tends to flow inwards towards the body. And when the air flows below the wing, it tends to flow away. Now what happens is that these two airflows meet at the wing tip, and when these two uh, types of flows meet at the wing tip, it produces vortices. Something like, in now look at this figure. Imagine if both ends are not fixed. So you have vortices produced at both the tips, right? And these vortices tend to move in the wake, in the trailing edge of the wing. So it produces this flow in the wake of the wing, right? So this is why vortices are generated. And now when vortices are generated, what happens is that there is an increase, there is a change in angle of attack at the tip. So throughout the wing, it's almost a uniform angle of attack. At the tip, because of this generation of vortices, there is a different angle of attack. It is an induced angle of attack. Because of this induced angle of attack, so if your Fy is something like this, and just a minute, let me just erase that. So if this was your velocity, it produces lift perpendicular to it, drag like this, and this is lift. And at the wing tip, there is this induced angle of attack. So it produces one component of lift, or it tilts the lift towards inside. Okay. So because of this, there is an additional drag component, di. Okay. So it's only at the tips that these are witnessed. Now the question said, what is the induced drag for an airfoil, not for a wing? So now can you try and think about it? How is an airfoil different from a wing? What is an airfoil? So it's the cross section of the wing, right? Right. So that is how the airfoil is different from a wing. Now these vortices are produced at the wing tips. So because of the vortices, you have an induced drag. So now just look at this question. Induced drag for an airfoil. 0? Yes. So our equation was CD is CD naught plus KCL square. The CD naught is parasitic drag, that's always there. Induced drag is this component. Now this CL is the lift produced by a wing, by a 3D wing. So for an airfoil, so the difference, if you've done the, I think, air performance course, a sir would have mentioned two types of coefficients, CL, small letter CL, or he would have written CL2D, and CL, that is for 3D. So here the value that comes is CL3D, it's a C capital L. Okay, so for an airfoil, that value doesn't exist. So there are no vortices produced at the tips of a airfoil. Airfoil is a 2D cross section of the wing. It's also referred to as a wing of infinite span. So what happens if you have infinite span is that you have no tip. And if there are no tips, there are no wingtip vortices. And if there are no wingtip vortices, you have no induced drag. There is no change in the angle of attack, there is no induced angle of attack, there is no induced drag. So this term becomes, that KCL square becomes 0. So induced drag for an airfoil is 0. Wing, yes, you're right, it's finite but not 0. For a wing, you always have wingtip vortices and they always produce a drag. Okay, is it clear? Let's go to the next question. Among the following, which aircraft instrument measures the altitude and speed respectively? Option A, yes. Altimeter and pitot. Altimeter measures the altitude and pitot measures the speed. What does the magnetic compass measure? Points to the north. Okay, so it measures the direction. What is that term called? What does it measure? It points to the north. So what quantity does it tell the aircraft about the aircraft? Orientation, heading. Yes, so Shreyash is right. It gives you the heading. Magnetic compass gives you the heading. What does the gyroscope tell you? There are many gyroscopic instruments. So, uh, one of them, let me just, yeah, so the first figure gives you the altimeter equations and the other figure gives you pitot. So just leave the boxes. So this is one of the gyroscopic instruments, this figure. So just look at these two figures and try to tell me what do gyroscopic instruments measure. Magnetic compass gives you heading. This is a magnetic compass. So if you are going straight, it points towards the north. If you're deviating from the north, it gives you by how much you're deviating from the north. So that is magnetic compass. This is magnetic compass. This is one of the gyroscopic instruments. So what do you think it measures? Inclination. How do we define? Yeah, so here it's giving you roll. So what gyroscopic instruments measure is the orientation. Right here, with respect to horizon. Okay, yeah. So it gives you the orientation, right? In this case, it's measuring the roll with respect to horizon, but other instruments measure the other orientations. Somebody said stability. So what measures stability? Can anyone tell me? Somebody had just pointed out stability when I asked about gyroscopic instruments. Can you just tell me what measures the stability of an aircraft? We just discussed the stability is the static stability is the initial tendency to come back towards equilibrium. What quantity measures that? Or what instrument or quantity or what how do we measure stability? How do we quantify stability of an aircraft? Just try to think about it. So what so if I am flying, let's just take the longitudinal case. I am flying in a steady level and I am encountering a gust and it deviates from my equilibrium point. So if the aircraft tends to come back to equilibrium, I am telling that it's a statically stable aircraft. Okay, so what structure on the aircraft brings it back? What component of the aircraft brings it back? Just try to think. Yes. I didn't hear you. Can you just repeat? Think about it. Think about it. Just the longitudinal. Longitudinal is the pitching moment. Okay. So we just mentioned the pitch. Okay. What generates this pitching moment? So let's just focus on pitching moment right now. What generates this pitching moment? Yes, you are right. So I am flying like this. I encounter a gust. If I have to come back, I need a pitching moment, pitch down. So what gives you this pitching moment? Elevator is okay. Elevator is a control surface that changes your pitching angle, right? So if you want your horizontal stabilizer, horizontal tail, right? So the inherent quality that brings it back to equilibrium or tries to bring it back to equilibrium is the tail, right? This elevator is on the horizontal tail, and when you deflect the elevator, you change the pitch. That is when the pilot wants the pitch to change. When you want to climb or something, and he wants to change the pitch, he deflects the elevator up or down, and the pitch angle changes. But what structure brings it back to equilibrium is the tail, correct? So in the longitudinal case, it's the tail. So somebody had mentioned that gyroscopic instruments measure stability. Uh, I, I don't think that's true. It doesn't measure stability, right? What measures stability? Yes, you're right. The pitching moment produced by the tail brings the aircraft back to equilibrium. But what quantity measures stability? How do you quantify it? Aircraft is very stable, less stable, unstable. What is that quantity? Or do you have instruments to measure it? CM naught. Okay. Any other answers? Delta E is the elevator deflection. So one thing, let me just clarify it. The control surfaces, the control angles, all of them do not contribute towards stability in any way. Okay. So, uh, so delta E deflection is the deflection of elevator. That only contributes towards changing the pitch angle. That is the control of the aircraft. That's when the pilot wants to change the pitching angle. Okay, so it does not contribute towards stability. It contributes towards controlling the aircraft. Okay, so okay, I think I have a slide about this somewhere along the line, but think about it. Think about what measures stability, what quantifies stability. I do have a slide about this in the future, so we'll just get to that. But think about it in the meantime. We'll just move on to the next question. Think about what quantifies stability, what tells you the aircraft is stable or unstable statically. Okay. So this is one question. If the weight of the aircraft is 1000 kgs and lift to drag ratio is 15, what is the thrust required in Newton at cruise condition? I think it's a fairly simple question. Let's just write down the quantities. So weight is 1000 kgs. Immediately just write down gravitational constant. Just a minute. Okay. So it's not given in Newton, so just immediately put that 9.81 so you don't make a mistake. Then they've given you lift to drag ratio, which is 15. Okay, and then they've asked you to find out thrust required. Thrust required formula we had seen in the very first slide. Can you try and solve this on your own? I haven't solved it. Let's try doing it together. Okay, try solving it. What was the formula for thrust required? Yes. It's a straightforward substitution. So try doing this and tell me the answer. 654. 654. Okay. So that is the right answer, 654. Okay. Now, yeah, so this is just the formula that we have used. I just put up a slide for that. Okay. I think this is where it comes up. Okay. Stability producing component of an aircraft. We just discussed this. What is the stability producing component? Tail. Okay. So, okay. So, if this is your fuselage reference line and you have a wing here and you have your horizontal tail here, okay, and this is your CG. Now, if the aircraft is subjected to a gust, it deviates from its initial position. So, I'll just draw the deviated position. So, it's something like this, okay. So, this is the deviated angle and you want it to come back here. You want it to come back to equilibrium point, okay. So, both the wing and the tail are producing lift, correct? There is a lift here, there is a lift here, correct? So what moment does the wing produce? This is the wing and this is the tail. Does the wing produce counterclockwise or clockwise moment about CG? Clockwise. So, and this is the equilibrium position, okay? You want it to come back here. So does the moment produced by wing bring the aircraft back to equilibrium? You want it to come back to equilibrium. Your aircraft, you want it to come back to equilibrium. So does the moment produced by wing bring it back to equilibrium? No. It produces a moment that is further deviating from the equilibrium point, right? It produces the moment in the opposite direction. What about the moment produced by tail, clockwise or counterclockwise, about CG? Counterclockwise. So does that produce a restoring moment that brings the aircraft back to equilibrium point? Yes. So the lift produced at the tail produces a counterclockwise moment, which will push the, it will give you a pitch down moment, right? It will bring the aircraft back to equilibrium point. It will try to bring the aircraft back to equilibrium point, correct? Correct. Okay, so that is how the tail contributes towards stability. I think, yeah. So this is the slide. So this is the pitching moment equation. Cm equals Cm naught plus dCm upon d alpha into alpha. Somebody had said Cm naught is the quantity that measures static stability. What is Cm naught? So your graph is something like this. Moment at zero angle of attack. So that moment is always there. It is produced mainly due to the cambered airfoil having some moment, right? Okay, let's start with that. So so this is your symmetric airfoil, and this is your aerodynamic center. What is aerodynamic center? Pitching moment is independent of angle of attack. Okay. What is center of pressure? CP. Yes. So it is the point at which the aerodynamic forces are actually acting. Correct? So for our ease of, and this point center of pressure keeps changing as your airfoil keeps moving up and down, which is why we came up with aerodynamic center, which is a point that is constant with angle of attack. Okay, so our analysis becomes easier. That is why we came up with aerodynamic center. Now when we transfer the forces from CP to AC, it will also come with a moment, correct? So you have some, this is CP and this is AC. So your lift and drag are actually acting at CP, and when you bring it to the aerodynamic center, it comes with a moment, correct? So that is the major contributor towards this Cm naught. Okay, so that is always there. Okay, and for a symmetric airfoil, there is no Cm, because the aerodynamic center and CP of a symmetric airfoil are the same point. It doesn't come with a moment. So the Cm naught for uh, the symmetric airfoil is not existent. Okay, it's zero. Now, the only quantity for the longitudinal case, the only quantity that measures static stability, or the only thing that tells you whether the aircraft is statically stable or not, is this dCm upon d alpha, the slope. Okay, if the, and the slope has to be negative. Why? Because when you produce, the aircraft is flying at a regular angle of attack. Due to gust, your angle of attack increases and you want to reduce it. So you need to produce a pitch down moment. That is a negative moment. So for a positive change in angle of attack, you need a negative moment. So your dCm upon d alpha becomes negative. Okay, so if it were positive, the aircraft would not come back to equilibrium. It would further keep deviating and it's not a stable aircraft. So the only condition for static stability, longitudinal static stability, is that your dCm upon d alpha should be less than 0. That is the only condition. So the quantity that measures stability is this dCm upon d alpha. It's called stability derivative. And you have one for each direction. For longitudinal case, it's the pitching moment derivative. Okay? Yes. 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 What we desire as in CM naught should be positive only. I mean, it's not mandatory. Okay. Why would you prefer CM naught does not contribute towards stability in any way? So the only reason why we want CM naught to be positive is because you want to trim at a positive angle of attack. It's just desirable. It's not necessary. So even if it's larger or lesser, it does not contribute towards the stability. The only quantity is the slope. So as long as the slope is higher slope, we desire higher slope. CM naught should be positive. Not should be, it's preferred to be positive. Yes, CM alpha should be more negative. Yes, correct, correct. That will be more statically stable. Okay. Now let's just look at the two main components of the aircraft, the wing and the tail, as far as longitudinal stability is concerned, and let's just look at their contributions towards Cm naught and Cm alpha. So the main equation is this: Cm equals Cm naught plus dCm upon d alpha into alpha. Now look at the wing contribution. So I've just split it in terms that are dependent on alpha, terms that are independent of alpha. Okay, so this is the Cm naught contribution of the wing, and this is the Cm alpha contribution of the wing. Okay, so now we want our Cm alpha to be negative. Just look at the Cm alpha wing and tell me if it will be positive or negative. Cl alpha, let's look at each term. Okay, so what is Cl alpha? It's the lift curve slope, right? Will it be positive or negative? Typically, for a typical aircraft. Positive. So this is positive. Then what about XCG minus XAC? For a typical aircraft, your wing is somewhere here. This is your CG and this is your tail. Okay, so the AC is approximately quarter chord length. So from the leading edge, it will be somewhere here. So this is the AC of the wing. So will XCG minus XAC be positive or negative? Positive. Yes. So the entire contribution, that is Cm alpha contribution by the wing, is positive. This entire thing is also positive. So Cm alpha wing is positive. Correct? So it does not contribute towards stability. In fact, it's destabilizing in nature. Correct? We had seen this even in the figure that I had drawn here, that the wing produces the moment that is not restoring. It's in fact producing the opposite moment that we desire. Okay, so wing is a destabilizing component for longitudinal stability. Now let's look at the tail contributions. So this is Cm naught contribution of the tail, and this is Cm alpha contribution of the tail. Now let's look at each term. What is VH? Does anybody know what is VH? Tail volume ratio. What do you remember the formula? What it? Okay. Okay. So it was area of the tail upon area of the wing into LT by C. C is the chord. What is LT? This LT tail moment arm. And so in this figure, can we try, this is the aerodynamic center of the tail. Okay, so tail moment arm is XAC tail minus XCG. So is that term positive or negative? Positive, correct. This is XCG and this is XAC tail. So this is positive. So entire BH is positive. So this is positive. Tail efficiency factor, again positive. CL alpha tail, again positive. What is this 1 minus dou epsilon by dou alpha? What is epsilon? Downwash, correct. So dou epsilon by dou alpha is generally a quantity that's less than 1. Not generally, it's always less than 1. So 1 minus that small quantity, again it will be positive. Okay, so this will also be positive. So this entire thing, CM alpha tail, because of this negative sign, is negative. So the tail produces a stabilizing factor. So it produces dCm upon d alpha is negative. So this is less than 0. Correct? So all that you have to remember for static stability is that dCm upon d alpha is less than 0. That is the only condition for longitudinal static stability. Cm not greater than 0 is something that we desire because we want to trim the aircraft at positive angle of attack. It's not mandatory. The only mandatory condition is that Cm alpha should be less than 0. Okay, so that is what quantifies that stability derivative is what quantifies stability. In the longitudinal case, it is Cm alpha. In the other cases, you have the other stability derivatives. Okay, so that is what measures the stability of an aircraft, not any instrument or not any other quantity. I just wanted to clarify that. Okay, let's move on. If an aircraft is in static equilibrium, it means aircraft controls are set to 0. Aircraft controls are not set to 0, may or may not be 0, none of these. Just think about it. Take a minute and think about it. Aircraft is in static equilibrium. Okay, why do you say that? Okay. All right, okay. Does anybody have any other answers? Okay, so if the aircraft is in static equilibrium and the control surface is deflected, if it's already in equilibrium, it will remain there. So it doesn't matter. The control surface deflection does not matter. You are right. It does not matter. It does not tell you anything about the equilibrium. So it can either be 0 or not be 0. If it's in equilibrium, it will tend to remain there. Okay, so it may or may not be 0. Okay, next question. If the weight of an aircraft is 1000 kgs, lift to drag ratio is 15, wingspan is 10 meter, and mean aerodynamic chord is 1 meter, the aircraft flying at a speed of 50 meter per second in mean sea level atmospheric condition, what is the lift coefficient at cruise? Let's just write down the quantities that we have. So weight is 1000 into 9.81. Lift to drag ratio is 15. Wingspan. What is the notation? What is the term for wingspan? I did not hear you. B, yes. So B is 10. Mean aerodynamic chord is 1. Flying at 50 meter per second. Mean sea level, so density is 1.225. What is the lift coefficient at cruise? How do we find this? How do we find this? Okay, Okay, so you can directly use lift equals half rho v square SCL, and you need to find out CL, and it is cruise, so lift equals weight. So CL is 2W by S rho v square. Can you compute this and let me know what the value is? One 1.7. Can you just verify that? Isn't 1.7 a little too high for lift coefficient? We know W, right? W, and you assume a rectangular wing, 0.64. Did everybody get that? So it's 2 into 1000 into 9.81, and it's W by S. S, I'm taking B into C. So S is B into C. So that's 10 divided by density is 1.225, 50 square, and that you get 0.64. Yes, everybody's getting 0.64. Yes, okay. So just when you get your answers somewhere greater than 1, just check again, because coefficient of lift is typically in this range, right? 0.5, 0.6, it's that range. So that's how you verify your answers. Yeah. Also check the units. Even I think in the assignment there was some confusion. Please check the units. Okay, so these are the formula that we used. Okay, the temperature ratio at 16 kilometer and 12 kilometers. So they've asked you the ratio of temperature at 16 by, so this is the ratio that they've asked. What would the value be? Just remember, recall the standard atmospheric model that we just went through. Do you remember the standard atmospheric model? I'll just, okay, so this was, yeah, so this was the model. If you look at this, can you tell me the ratio between temperature at 16 and 12? Yes, Shreyas has said 1. Does anybody have any other answers, or does anybody want to justify that? Did somebody say something? Okay, couple of people have got 1. Does anybody want to, either of you, do you want to tell everyone how you got 1? Okay, as T16 and T12 are equal. Yes. So the temperature at 12 is something here and 16 is somewhere here. So the temperature remains constant in that region. Lapse rate is 0. So the temperature in both those regions are the same value. Hence the ratio would be 1. Correct? So T16 by T12 would be 1. It's the same temperature. Correct. Okay. Aircrafts can be classified based on. So there are several different ways in which we can classify an aircraft. So the answer would be all of these. It would be all of these. You can classify aircrafts based on different criteria. So let's just go over some of the basic classifications. Based on total weight of the aircraft, we have lighter than air and heavier than air. Heavier than air is almost every aircraft that we know, heavier than air. Can anyone tell me what lighter than air would be? Any example? Does it have to be an aircraft? Just anything that's lighter than air? Sorry? Glider will not be lighter than air. But yes, balloons. Glider will not be lighter than air, right? It does have mass that's greater than the mass of the air. Correct? So yeah, balloons. Then, depending on the size of the aircraft, we have micro airplane, single seater, double seater, medium aircraft seating 50 passengers, large aircraft 400 passengers, cargo aircraft, all of those things. Then, based on the mode of operations, commercial, non-commercial, or military, based on whatever mission that you're going for, you have different classifications of aircraft. Okay. Then you have, this is one of the typical classifications, speed of the aircraft. Subsonic, transonic, supersonic, and hypersonic. Can someone tell me what ranges of velocity or what ranges of speed each of them are? Subsonic is? Subsonic is? Yes, so less than Mach 1, right? Less than Mach 1, less than 1 Mach. Transonic is in the transition region. That's between zero point 0.8 to 1 point, right? So it's in that transition region. So let's just take somewhere around zero point 0.8 Mach. Then supersonic, greater than 1, right? Greater than 1 Mach. It's between 1 and 5 Mach, and hypersonic is greater than 5 Mach. Can you give me an example of hypersonic vehicles? Can you give me an example of supersonic vehicles? Fighter aircrafts, correct. What about hypersonic? Exactly. Yes, hypersonic vehicles are those rockets, especially during re-entry where it's greater than I think 20-25 Mach. So hypersonic vehicles are rockets, correct. Then, based on the type of engine, you have propeller-driven aircrafts. Then you have turbojet, turbofan, ramjet, and something known as scramjet. That's supersonic ramjet. You have different types of engines. Then, based on the number of wings, monoplane, biplane. What is one of the most famous examples for biplane? Like the first aircraft ever made, the Wright brothers, that was a biplane. So, depending on the number of wings, sets of wings, okay? So, one pair, monoplane, two pair, biplane, you have triplane and many other classifications, many other categories. So, these are some of the basic classifications of aircraft. So, there are several other categories. Do feel free to go and explore all of them. So, this is just the basic, some of the things that I thought we should be going through. Okay, next question. Okay, during a flight, due to passengers' movement, the center of gravity of an aircraft moves away from the neutral point. Due to this, the elevator angle required to trim the aircraft will be. Have all of you done the stability control? Can you speak a little loudly? I can't hear you. I'm not done complete lectures. I've done only 5 to 6. I'm not sure if is the stability control course marked as a prerequisite. Okay, so let's just, okay, we'll go through some, the basic longitudinal stability was what we had seen in that slide. So now here, one of the equations that we know is this delta E trim. Okay, that is the elevator deflection required to trim the aircraft at any CL. So you want to trim at 0.6 CL, plug in 0.6 CL into this equation, and then you get how much elevator you should deflect. Okay, so this is the equation that gives you how much elevator to deflect to plug at different CL, I mean to trim at different CLs. Okay, so this is the graph of this equation. So if your one of the main quantities you can see here is the XNP minus XCG. Okay, so if your CG is at the neutral point, you will have no slope. So this line corresponds to XCG equals XNP. And then you have CG1, CG2, CG3, which move away from the neutral point. So if this is your fuselage reference line, this is your neutral point, this is CG1, this is CG2, this is CG3. As your CG moves away from the neutral point, the slope, the magnitude of the slope keeps increasing. Okay, it's a negative slope, but the magnitude keeps increasing. If your CG is at the neutral point, you have no slope. Okay, so now look at the question. It says during a flight, due to passengers movement, the CG moves away from neutral point, right? So just look at the question carefully. We'll go back to the graph. CG moves away from neutral point. Okay, so let's just presume the first CG was CG1. Okay, and now the passenger has moved and the CG has moved away from the neutral point. So this is CG2. Okay, so now let's just say the trim value that we required, CL trim, was something here. CL trim, it's any value that we require, that we want to trim the aircraft. What is trim? What was trim?
Where net moment is 0.
Yes, where net moment is 0, correct. So suppose I want to trim my aircraft at this CL trim. Okay, so let's just draw a line there. Okay, so now C for CG1, this is CG1 and this is CG2. The elevator required to trim at CL trim for CG1 is this, and CG2 is this. Which is more? Delta E1, delta E2. Which is more? So delta E versus CL, that is our graph, right? So the delta E required to trim for the first CG is delta E1. For second CG is delta E2. Which is more?
Delta E2.
Delta E2 is this value, right? You see? Let me just take a different color or something. So this is delta E2, correct? Blue color. Delta E2 is in blue. And delta E1 is in red, which is larger. Delta E1 is larger. So when the CG moves away from the neutral point, delta E required decreases, correct? Correct? Is that clear? Okay. So this is an equation that we have learned in the stability control course. So every time something like this comes up, please do refer to the lecture notes or the lectures of that course. Okay, stability control, aircraft stability control. Okay, let's move on. Again, a similar question to the previous one. The primary control used for angle of side slip control of the aircraft is? What was angle of side slip? So angle of attack was the angle made by V infinity to the chord line. Angle of side slip is the angle made by V infinity to the fuselage reference line. So this is beta. So V infinity was originally here. Due to a gust, it has moved sideways and then it has produced a side slip angle beta. Okay. Is that something, again, is that something we can control? No, right? Because the V infinity moved sideways, you have a side slip. But it's not something that we can control. What we can control is the yaw. So aircraft is moving like this, like oncoming velocity. Okay, let me just. So aircraft is moving like this, and then it had to tilt. It encountered a gust and it encountered a side slip angle. So what do we do to bring it back? We yaw the aircraft, right? We yaw the aircraft. So it should have been primary control for yaw. Side slip is not something we can control. So what is the primary control for yaw? Rudder, correct. So yeah, so I have this figure that gives you the difference between side slip and yaw. Though it looks very similar, they are different angles. So yaw is you're flying your aircraft straight with respect to some reference frame, and then you yaw it, you turn it, right? So with respect to the reference azimuth, reference frame that we have taken, it produces an angle. You are changing the direction of the aircraft. So So that is yaw. What is side slip? The aircraft was originally going straight, encountered a gust, the oncoming velocity's direction changed, right? So that is angle of side slip. Though it looks very similar, it's not the same thing, right? Can you see that the aircraft in one case is remaining the same? The fuselage reference line is the same. This is the fuselage reference line. The direction of velocity has changed. That is side slip, where we are turning our aircraft with respect to some reference frame. That is yaw. That is the angle that we can control. Roll, pitch, yaw. These are the angles that we can control. Okay, so there is a difference between yaw and side slip. Just like there's a difference between angle of attack and pitch. Okay, is that clear? Okay, so the question should have been, just like the previous case, it should have been control for yaw. Okay. Aircraft longitudinal stability depends upon. We just discussed this. Which one do you think is the right answer? Correct. So tail moment arm was LT. We saw that it featured in the equations, tail moment arm. So this was the equation for the tail contribution, right? And where does this LT come? Tail moment arm is the right answer. In this equation, it should feature somewhere, right? So where does it feature? Correct. So it comes in the tail volume ratio. Does the control surface area come anywhere in this equation? So tail volume ratio was VH, ST, LT, SC. ST is the tail area. Does the control surface area come anywhere in this equation? No, correct. Control surface area doesn't. So ST is just the tail area. A portion of the tail is the control surface, elevator. The whole tail is not the elevator. So the elevator area is not coming anywhere in this equation. Hence, control surface area doesn't contribute towards CM alpha. CM alpha is the only thing that measures stability. Okay. So control surfaces are to control the aircraft. So to control the attitude of the aircraft. Does not contribute towards stability. What are winglets? This first option, winglets. What are winglets? Vortices. Correct? Yes. So what were vortices? When the upward and the downward flow meet at the wingtip, it produces vortices. So winglets are, it reduces the, so I'm not sure if I can draw this. So when you see from behind or from front, if this is the wing, the winglet is something like this, right? So it tapers towards a point so that the vortice or the magnitude of the vortices are greatly reduced. Okay, so winglets are something that we introduced to reduce the wingtip vortices. Upward bend and it tapers towards a point. So the magnitude of the vortices generated greatly reduces. Okay, okay. So next question. During a maneuver, lift is 5 times the weight of an aircraft. If the trim velocity at cruise was 80 meter per second, what will the velocity during maneuver be? What was the trim velocity equation? Trim here in this case would be steady level flight, right? One of the trim conditions would be steady level. So that is when lift equals weight and thrust equals drag. In this case, what was V? This is the first case. So what was the equation for velocity for steady level? That is trim in this case. Under root W by S upon rho CL. And this is given to be 80. Now case 2 is when lift has become 5 times the weight. So you can just write V equals 5 W upon S by rho CL. So now I just take out terms from the equation. So it will be under root 5 W by S by rho CL. So this is nothing but under root 5 into 80. Correct? So that is the right option. Now let's look at the next question. These are the equations that we used to solve this question. Next one. During a mission, food packets are dropped, and as a result, the weight of the aircraft is reduced to 70% of its initial weight. What will be the new stall speed if initial stall speed was v? Similar to the previous question, can you tell me the answer? What is v stall formula? By rho CL max. Correct. So this is v stall. Okay. This question is very similar to the previous question. Can you tell me the answer? Just read it carefully and tell me the answer.
V times square root of the equation.
Correct. So it's very similar. In the previous case, you had the lift became 5 times the weight. Here, the weight is reduced by 70%. So it becomes 0.7. Okay? 0.7 into a V. That's all. Yes. Let's look at the next question. Generally, lift to weight ratio during takeoff will be very simple. Greater than 1. Correct. Because the lift should be greater than the weight in order to it lifting off the ground, right? So yeah. Next question. Do let me know if this is becoming too much. Okay, we can go a slow stop and do the next questions in the next week. Okay, so let's just look at this question. The drag polar of a propeller driven airplane is given by CD equals 0.05 plus 0.03 CL square. The lift curve slope of the wing is CL alpha is 0.1 per degrees and zero lift angle of attack, that is alpha at lift equals 0, is minus 1 degrees. So is it, what kind of airfoil is it? Positive camber. Prajwal has raised a hand. Do you have a question? Okay, okay. Yeah, so it is a positively cambered airfoil because you have, so it says, so this is your lift curve slope. See, and now they've given you an angle of attack at zero lift. So that means it's here, right? So this is the angle of attack at zero lift. Correct. So it is a positively cambered airfoil. Okay. The lift to drag ratio or the aerodynamic efficiency at minimum power condition will be. How do we compute this? They've asked you lift to drag ratio, that is L by D or CL by CD. Okay. So let's just individually compute CL and CD and take the ratio. How do you get CL? What is the formula for CL? Minimum power, it is under root of 3 times CD naught by K. So what is the value here? What is CD naught? 0.05. Correct. And K is 0.03. Correct. Okay, so what is the value of CL? Root 5. Can you tell me the value? 2.23. Okay. And what about CD? What is the equation for CD? For minimum power condition. 4C. Correct. So it is 4 into 0.05. So now can you tell me what CL by CD will be? 11. I haven't calculated this. See if everyone's getting the same answer. Okay. So Shreyasha said, okay. 11.15. Fine. So that is the value. So 11. Correct? Okay. Now let's look at the next question. So yeah, these were the equations that we used to solve this. For minimum power condition, this is what is maximized. CL raised to 3 by 2 by CD. Okay, so I've just written that down. Next, same question. A lift to drag ratio at maximum range condition. Maximum range was what? What was the condition equivalent to maximum range? So the previous question was minimum power. That was maximum endurance.
C not by K.
Yes. CD naught by K. Yeah, so yes, it's referred to as minimum drag or minimum thrust required. This corresponds to maximum range. Okay, so what will the value here be? Under root 0.05 by 0.03. 1.29. Okay, and CD here will be 2 CD naught. That is 2 into 0.05. So what will L by D be? What was this value? 12. Okay, 12.91. Okay, so that is the right answer. I haven't pleased to see if everyone's getting the same answers. Okay, let's move on. Yeah, so these are the formula that we used. For maximum range, CL by CD is maximized. That is minimum drag or minimum thrust required. Okay, now same question. The ratio of aerodynamic efficiencies at minimum power and maximum range. Very simple, just the ratio of those two conditions. Okay, just do that. So you have CL by CD by CL by CD, and this was minimum power and this was minimum drag. Just the ratio of those two values. Okay, you can do that. Let's just move on to the next question. The angle of attack in degrees of the aircraft for maximum range condition. How do we do this? Angle of attack of this aircraft for maximum range condition. We have the CL at maximum range. So what quantity? It's the same. The data is the same. Okay. So CL for maximum range or minimum drag, we have, what was the value? This is the one, right? So it's 1.29. So this is the data that we have, and they've asked you for angle of attack at this condition. How do we find that?
0.1 CL per degree.
Okay. Can you tell me? Okay. So this is given. CL alpha is given. Correct. So what equation do I use? What equation do I use? We have these two quantities. You have the CL at minimum drag, maximum range condition. You have the slope. Now what do we do? Just think about it. They've asked you to find angle of attack. CL alpha is in per degree. CL is a non-dimensional quantity. So what equation do we use these two quantities in? So we have CL, we have CL alpha, we have, and we are asked to find alpha. So this is what we need to do, correct? So what equation do you think we can use? What equation can we use? Just think about it. It was one of the most basic equations that we have used, we've discussed in this lecture. I think it's the first equation that we had discussed in the lecture. You have the lift coefficient, you have the lift curve slope, you need to find out angle of attack. What equation connects all these three? What is the equation for CL of an airfoil?
not plus VC.
Correct. So CL is CL naught plus DCL by D alpha into alpha. You have CL, you have the slope, you need to find out this. Before that, what else is missing? You need to find out CL naught. How do you find out CL naught? So this was your CL versus alpha. You have this quantity that is minus 1 degrees. This is your CL naught. Correct? How do you find out CL naught? CL naught. From this graph, it's a straight line, it's a linear line. So how do you find out CL naught? Just you have 2 points, it's a straight line. You need to find out the coordinates of 1 point and you have the slope. So it's just you take those 2 points, you have 0 minus of minus 1 into CL alpha, right? Correct? So just equation of a slope of a straight line, okay? So it will just be 0 minus of minus 1 divided by CL naught, correct? CL naught minus 0. Is this making sense? Okay, yeah. So you just plug these values in and then you can find out your CL naught. So that is how much CL naught? It will just be 0.1, correct? Okay. And then from there you use this equation. So it gives CL is 1.29, CL naught is 0.1, DCL upon D alpha is again 0.1 alpha. So how much is alpha? Okay, I haven't computed it, but 0.12, okay. Did you understand how we solved this? Okay, can you just verify it? How much is it? 11.9. Okay. Alright.
Sorry, man. Yes, sir.
Alright. Okay, so 11.9 degrees is the final answer. Did everyone understand how we solved this? So you had CL, you had computed CL in the previous question. You have the lift curve slope and you had to find out the intercept CL naught. Using these three values, you use your lift curve slope equation, the lift slope equation, right? Lift curve equation. Okay. And from there, all the quantities are known, only alpha is unknown. Plug in the values, find out alpha. That's all. Okay. Okay. So I think with this, we'll end today's session. Does anybody have any questions? Any doubts? Yes, please ask Ajay. Design the winglet. I don't think there are any such parameters. It's just you smoothen out the flow from, like, if it was a sharp wing tip, the flow intercepts at this point and at that point there is a instability, correct? So you just smoothen out the flow, you reduce the magnitude of the flow at the intersection. So it's just that. It will have the basic cross section will be same. It will still be an airfoil cross section, just of reducing length. So it will be tapering. So it will be reducing chord, but it will have the same airfoil cross section. Maybe narrower. That's all. Okay, that we'll have to look into it when we get into the aspect ratio. When we get into designs, we'll look into that. I'm not sure as of now. Sharan, you had a question? CL naught. Okay. So let me just, I'll just erase this and solve this. Great. Okay. So this was your lift curve slope, CL versus alpha. This is CL naught. This quantity is -1. Okay. Till here it's fine. Okay. Now let's just take these 2 points. It's a straight line and let's just take these 2 points. So the slope is CL alpha is 1 second, somebody wants to join the. Okay. So for a straight line equation, what would the slope be? It's y2 minus y1 by x2 minus x1, correct? Okay. So in our case, let's just take this as 1 and this as 2, points 1 and 2, okay? So what, and y here is CL, in the y-axis you have CL, in the x-axis you have alpha, alright? Okay, sorry, it should be x2 minus x1, sorry. 1 minute. Let's erase this. Okay. So what would the values be? At point 2, at the location 2, what would the value of alpha be? Value of alpha at location 2 at this point. It will be -1, right? -1 minus what is the value at point 1 alpha? 0. Correct. Then at point 2, what is the value of CL? 0. Minus what is the value at point 1? 1. Now you just substitute this and you can find out the CL alpha we have, right? Wait just a minute. At point 1, what is the value of CL? At point 1, what is the value of CL? Somebody said 1. That's not right. What is the value of CL at point 1? This is point 1. What is the value of CL? CL naught we have not found yet. This is the process for finding CL naught, correct? Okay. And we have this. Okay. Again, it's the reverse of this. Let me just start all over again. I'm sorry, okay? I'll just start all over again. So what is the value of CL at point 1 or point 2? What value of CL at point 2? 0, correct? Value of CL at point 2 is 0. Value of CL at point 1 is CL naught, correct? Similarly, what is the value of alpha at point 2? It's minus 1. Minus value of alpha at point 1 is 0. Correct? And this value we know as 0.1. CL alpha is given as 0.1. You just substitute, you get CL is 0.1. CL naught is 0.1. Okay. Any other questions? Any other questions? If you have any other doubts. Okay, if there are no other questions, then I think we can end the meeting here. We'll meet on Tuesday before your assignment. So all the very best for the assignment, and we'll meet on Tuesday. Thank you. Thank you.
Thank you.